Okay guys, today we're going to start our last chapter of the year. It's on waves and optics. Today's lecture though is just going to be wave basics with incorporating sound into it. So if you look at our first slide here, what is a wave? Waves have one job, and their job is to simply transfer energy. They do not transfer matter. We have a couple categories of waves that we're going to analyze and look at. The first category are your mechanical waves, and they require a medium to propagate. And a medium is just a fancy word for material. So for example, a mechanical wave needs a solid, liquid, or gas to move. A great example of a mechanical wave is sound. The other category of waves are called non-mechanical waves, and the big difference is they do not require a medium to move. And the example I have here are called EM waves, and I will talk about what EM waves are in a couple slides from now. Waves in general can be made up of a single pulse, or a bunch of or series of pulses, or often what we call pulses are your disturbances. So let's take a look at our mechanical waves here. As I said before, they do need a medium, and the biggest example I can give you of a mechanical wave is good old sound. Hence, when you are in space, nobody can hear you scream. And that is because when there is space, there is no medium. So therefore, sound cannot travel through the space. The other category of waves are your non-mechanical waves, as I talked about on the previous slide. And I said on the previous slide that those are called EM waves, but I'm going to actually write out the whole word here. Examples are your electromagnetic waves, and just to list a few, those are your radio waves, those are your UV waves, those are your visible light waves, those are your X-rays, and gamma, and the list goes on and on and on. All I've mentioned here is light because that is going to be the main focus that we talk about when referring to non-mechanical waves. Alright, sticking with our wave basics here. Now we have different shapes. So I like to call these the two main shapes that our waves can take on. So once again, we have a transverse shape. And you can read the definition there. The motion of energy displacement is perpendicular to the direction of oscillation of the medium. And then in this diagram are just the pieces and parts of a transverse shape. So you can see the crests are your top parts, your troughs are your bottom parts. Wavelength is the distance from one point on one wave to the point on the next. And then lastly, your amplitude, I like to call it the height of your wave that goes from your what we call the rest position, which is your horizontal line, on down to the trough, or it can go from the rest on up to the crest. And then one key word I want to bring back into this unit is period. And period has a symbol of T. And remember, the unit of a period is S for seconds. And if you recall, that is the time for one wavelength. So the time it takes for one wavelength to pass through. And as you can see, it's diagrammed on here for you. The other type of shape is called a longitudinal shape. And you can see the definition right below it. The motion of energy displacement is parallel to the direction of oscillation of the medium. And some examples here are your pressure waves. And of course, your good old sound waves. And it's these alternating pressure regions in sound waves that cause vibrations of our eardrums that allows us to hear. If you go back up here, the examples of your transverse shape are all of your EM waves, your electromagnetic waves will take on that shape. All right, so what you're going to do right now is you're going to go ahead and you're going to click on video number 1 in Google Classroom, and all this video, it's a very, very quick one, maybe 10 seconds at the most. All this video is going to show you is an example of what a longitudinal shape looks like. So you can go ahead and click on video number 1. Okay, so to summarize these wave parts that I just talked about a couple slides ago, we talked about the wavelength, which was the distance between corresponding parts on adjacent waves. I went ahead and I showed you the crest, which is the highest point. I showed you the trough, which is your lowest point. I showed you the amplitude, which is your max height above or below the rest position. And then lastly, we have this a lovely equation here that deals with waves. It can get us the speed of a wave. So as you guys know, V is for velocity. Your F is for frequency. And this upside down looking Y, that is your wavelength. So what we're going to do now is we're going to transition into focusing on just the sound waves. So what we've done thus far is just the basics of waves in general. We talked about the 2 categories of waves and the 2 types of shapes that these waves can take on. So now the rest of the notes, like I said, is going to focus just on our sound waves. So, the basics with hearing sounds. So our normal range of hearing can go from 20 hertz to 20,000 hertz, and then we just have some basic vocab here. Below range is called subsonic. If you're above the range of hearing, that's called ultrasonic. And then the frequency and the volume are our deciding factors if we can hear something. And just to remember, to recall back to the beginning part of these notes, if we're talking sound, we are talking the mechanical category of waves, and we are talking the longitudinal shape. What I'm going to do when you guys are all said and done with these notes is I'm going to go ahead and pull up a frequency generator, and we're going to go ahead and test everybody's range of hearing to see if we truly can hear and what the experts say from this 20 hertz to this 20,000 hertz range. Talking about the speed of sound. What's nice is when we're dealing with the speed of sound, it is a constant, meaning that it's going to be the same value for a given medium. And as you see below right here, the speed of sound in air does have a dependence on temperature. So we have 2 values that we deal with. We have 330 meters per second for the speed of sound when at 0 degrees Celsius, or 343 meters per second when at 20 degrees Celsius. And 20 degrees Celsius is room temperature. So what we have next here is video number 2. So in just a minute, you're going to go ahead and pause these notes, and you're going to go ahead and watch video number 2 here. And what I want you to notice in this video is notice the airplane punch through the sound barrier, and then you hear the boom. And that is because light travels faster than sound. So go ahead and pause the notes at this point and go ahead and watch video number 2. Okay, let's look at the energy behind sound now. And this is a little bit of review back from our energy unit. Sound energy is the result of energy transformation, meaning that we have some type of conversion going on. If you look at my example here, speakers convert electrical energy to sound energy. We've all heard of the word power before, so power or loudness is related to how quickly that energy is converted. Now remember, sound waves are pressure waves, so their amplitude is related to their pressure and energy. Keep in mind, sounds too loud, that means the pressure is too high, and that's what ultimately could rupture or damage your eardrums. Okay, so now we have come to video number 3, and this video is just going to show you some fun examples of sound damage, because we just talked about sound. If it's too loud, it has too high of a pressure, and it's the pressure that ultimately damages those eardrums or causes them to rupture. So watch this quick video here and you can see the regions of high pressure and the damage that it causes. So go ahead and pause and please watch video number 3. And lastly, the last idea that deals with sound is the Doppler effect. And I'm pretty sure all of you have heard and are aware of the Doppler effect, but here is your definition of it. When a sound source moves or the detector moves, there is an apparent change in frequency of the sound. And the key word here is apparent. Biggest example, you can hear this in a passing ambulance, a passing cop car, passing fire truck, passing train. The examples go on. And then just some real life examples for the use of Doppler effect. We know our meteorologists use it, so the radar makes use of it. And then our good old astronomers also make use of the Doppler effect, but they're using light to determine if the objects are moving away or towards us. And then once again, when you guys are done with the notes, I have a quick little simulation that can just give you a good visual of this Doppler effect of the frequency and pitch and what's happening between them. And then lastly, our last 2 videos, and this video right here, video number 4, is just a fun one. It's the Big Bang Theory, the television show Big Bang Theory, and it's going to make use of and talk about the good old Doppler effect, so more of just a comical standpoint. And then lastly, down here, video number 5, once again, is making use of and showing the Doppler effect with a passing train. So you can go ahead and pause the notes here, and you can go ahead and watch video number 4 and video number 5. And at that point, that will conclude these intro notes on wave basics and just your basics on specifically sound waves. So there is a lot of concept in these notes, no math as you can see. So once you are done with these notes in the videos, you can go ahead and do day 1 homework.